If Betelgeuse replaced our Sun, Earth wouldn't just be uninhabitable. Earth wouldn't exist. We'd be vaporized inside a star so massive its surface would stretch past Mars. But here's what makes this even stranger. We're not entirely sure how big Betelgeuse actually is. Astronomers have been revising their estimates for decades, and what they've discovered challenges everything we thought we knew about measuring the cosmos. Look up at Orion's shoulder on a clear winter night. That reddish star marking the hunter's armpit is Betelgeuse, usually the 10th brightest object in our sky. It appears as a single point of light, barely distinguishable from thousands of other stars. Yet this dot contains a volume so vast that hundreds of thousands of suns could fit inside it. The disconnect between what we see and what exists is almost unsettling. Understanding Betelgeuse's true size isn't just cosmic trivia. This star will explode as a supernova sometime in the next 100,000 years, potentially within our lifetimes. When it does, it'll briefly outshine the full moon and be visible during daylight. Knowing its actual dimensions helps us predict when that spectacular death might occur. The story of measuring Betelgeuse begins on December 13th, 1920, when astronomers achieved something revolutionary. For the first time in human history, they measured the physical size of a star beyond our solar system. Before that moment, every star except the Sun appeared as an infinitesimal point, regardless of telescope power. We knew stars existed at vast distances. We could measure their brightness and color, but their actual physical dimensions remained complete mysteries. The breakthrough came through interferometry, a technique that combines light from multiple telescopes to achieve resolution impossible with any single instrument. When researchers aimed this technology at Betelgeuse, they found something extraordinary. The star had an angular diameter of about 0.047 arcseconds. That number means nothing to most people, so think of it this way. If you placed a dime in Los Angeles and tried to see it from New York, you'd need to resolve an angle roughly similar to Betelgeuse's apparent size from Earth. But here's where it gets complicated. That angular measurement tells us how big Betelgeuse appears from our vantage point, not how big it actually is. Converting angular size to physical size requires knowing the star's distance with precision, and that's where the problems begin. Measuring cosmic distances is notoriously difficult. The standard technique, parallax, works by observing how a star appears to shift position as Earth orbits the Sun. Closer objects shift more than distant ones, just like nearby fence posts seem to move faster than distant mountains when you drive past. For relatively nearby stars, this shift is measurable. For Betelgeuse, sitting roughly 550 light-years away, that shift is incredibly tiny and complicated by the star's variability. Different measurement techniques have produced wildly varying distance estimates. Some studies placed Betelgeuse at 400 light-years away. Others suggested 600 light-years. That 200 light-year uncertainty might not sound significant, but it creates massive discrepancies in size calculations. If the star is closer, it must be smaller to produce the same apparent size. If it's farther, it must be larger. A 2020 study using data from the Solar Mass Ejection Imager satellite produced what many astronomers consider the most reliable estimate yet: 548 light-years, give or take about 50 light-years. This measurement, combined with refined angular diameter observations, suggests Betelgeuse has a radius approximately 764 times larger than our Sun's radius. That's more conservative than earlier estimates that push toward 1,000 solar radii. But it's still almost incomprehensibly large. Let's put that number in perspective. The Sun's radius is about 432,000 miles. Multiply that by 764, and you get roughly 330 million miles. Betelgeuse's diameter, twice its radius, stretches to about 660 million miles. For comparison, Earth orbits the Sun at a distance of 93 million miles. Mars orbits at about 142 million miles. If Betelgeuse sat where our Sun is, its surface would extend well past Mars's orbit, reaching roughly 96% of the way to Jupiter. Every planet in the inner solar system would be gone. Mercury, Venus, Earth, Mars, all vaporized within the star's outer atmosphere. The asteroid belt, that collection of rocky debris between Mars and Jupiter, where millions of objects orbit, would be completely engulfed. Even Ceres, the largest object in the asteroid belt, would find itself deep within Betelgeuse's photosphere. Think about the spacecraft we've sent to explore the outer solar system. Pioneer 10 and 11, launched in the 1970s, traveled past Jupiter into the void beyond. Voyager 1 and 2 followed, now cruising through interstellar space billions of miles from Earth. If Betelgeuse replaced the Sun, these probes would still be inside the star during their Jupiter flybys. Volume comparisons make Betelgeuse's scale even more staggering. The formula for a sphere's volume includes the radius cubed, which means small increases in radius create massive increases in volume. A star with 764 times the Sun's radius has 764 cubed, roughly 446 million times the Sun's volume. You could fit somewhere between 446 million and over 1 billion suns inside Betelgeuse, depending on which size estimate you accept. Yet despite this enormous volume, Betelgeuse contains only about 16 to 19 times the Sun's mass. This creates a profound implication. Betelgeuse is extraordinarily diffuse. Its average density is somewhere around 0.000000002 to 0.000000009 times the Sun's density. To put that in perspective, the best laboratory vacuums on Earth are far denser than Betelgeuse's outer layers. In many ways, this star more closely resembles a hot, glowing vacuum than what we intuitively think of as matter. This brings us to a fundamental question. Where exactly does Betelgeuse end? Unlike Earth, which has a clear surface you could theoretically stand on, or even the Sun, which has a relatively sharp boundary between its photosphere and corona, Betelgeuse fades gradually from relatively dense inner regions to increasingly tenuous outer regions. There's no clear edge, just a continuous transition from definitely star to probably space. Different wavelengths of light see different surfaces. Observations in visible light penetrate to a certain depth in the star's atmosphere. Near-infrared observations see deeper, revealing hotter, denser regions closer to the core. Mid-infrared and radio observations detect the cooler, more extended outer regions. A 1996 study measuring Betelgeuse in one wavelength found a diameter of 56.6 milliarc seconds. A 2000 study using different wavelengths measured 54.7 milliarc seconds. These aren't measurement errors. They're detecting genuinely different layers of the star's structure. This wavelength-dependent size variation reveals Betelgeuse's complex, layered architecture. The star doesn't have one photosphere, but multiple atmospheric zones, each visible at different wavelengths. There's the core photosphere where most visible light originates, an extended chromosphere of slightly cooler gas above that. And beyond that, a vast circumstellar envelope of dust and gas that extends trillions of miles into space. That outermost envelope is so large that light takes about 2 months to cross it. Think about that. Light travels at 186,000 miles per second, covering nearly 6 trillion miles in a year. A region so vast that light requires 2 months to traverse it represents a scale almost beyond comprehension. This envelope isn't part of the star in the traditional sense. It's more like an atmosphere of ejected material, constantly replenished as Betelgeuse sheds mass through powerful stellar winds. Multiple shells of dust and gas surround Betelgeuse at various distances, each representing different episodes of mass loss. Studies have identified at least 3 distinct shells, with the innermost extending 50 to 150 times the star's radius, and the outermost reaching 250 times the star's radius. Using the 764 solar radii measurement, that outermost shell extends roughly 1,400 astronomical units from the star's center, about 35 times the distance from the Sun to Neptune. These shells drift outward at speeds of several miles per second, carrying material that was once part of Betelgeuse's outer layers into interstellar space. This mass loss is substantial. The star loses approximately 1 Earth mass of material every 10,000 years. Over its lifetime as a red supergiant, Betelgeuse has shed multiple solar masses worth of material, creating the complex circumstellar environment we observe today. But the story gets even more complicated. Betelgeuse doesn't maintain a constant size. The star pulsates, expanding and contracting over roughly 400-day cycles. During these pulsations, the star's diameter can vary by up to 60%. That variation, 60% of 764 solar radii, represents a change larger than the Earth-Sun distance. Imagine the Sun swelling to nearly twice its size, then shrinking back down, all while you watch over the course of a year. That's what Betelgeuse does naturally. These pulsations aren't gentle, uniform expansions. They're driven by violent convection in the star's interior. Unlike the Sun, where convection occurs only in the outer 30% of the radius, Betelgeuse's entire envelope is convective. Enormous cells of hot plasma rise from deep within the star, release their heat at the surface, then sink back down. Some of these convective cells are comparable in size to the star's radius. Imagine a bubble of plasma larger than Mercury's orbit rising through the star. High-resolution images of Betelgeuse's surface show these convective cells as bright hotspots, creating a mottled, irregular appearance rather than a smooth sphere. The star looks less like a perfect ball and more like a lumpy, boiling cauldron. These convective cells contribute to the star's variability, drive mass loss, and make defining a precise radius somewhat arbitrary. When the surface is constantly churning with features larger than planets, where exactly do you measure from? This brings us to one of the most dramatic demonstrations of Betelgeuse's dynamic nature, the Great Dimming of 2019 to 2020. In late 2019, Betelgeuse's brightness began dropping precipitously. By February 2020, it had dimmed to magnitude 1.6, still visible but noticeably fainter than normal. speculation ran wild. Was this the beginning of the long-awaited supernova? Were we witnessing the star's final death throes? The answer turned out to be even more interesting. Betelgeuse had ejected an enormous mass of material from its surface, roughly 400 billion times more massive than a typical solar coronal mass ejection, weighing several times more than Earth's moon. This ejected material cooled rapidly, forming a cloud of dust that partially blocked our view of the star. We weren't seeing the star dim. We were seeing it partially obscured by its own ejected atmosphere. The mechanism behind this ejection reveals just how violent Betelgeuse's surface can be. A massive convective plume over 1 million kilometers across rose from deep within the star and punched through the photosphere. The resulting shock waves and turbulence ejected a significant chunk of the star's outer layers into space. The ejected material cooled from thousands of degrees to hundreds of degrees almost immediately, condensing into dust particles that formed an obscuring cloud. This event demonstrated that Betelgeuse's size can change dramatically over short timescales, not just through pulsation, but through violent surface eruptions that temporarily alter the star's structure. It also showed how difficult it is to define what we mean by size for such a dynamic, turbulent object. Is Betelgeuse's size defined by its photosphere, its chromosphere, the extent of its circumstellar envelope? The answer depends entirely on what you're measuring and how. Recent observations have added another fascinating wrinkle to the Betelgeuse story. In 2025, astronomers announced evidence for a companion star, a previously unseen object orbiting within Betelgeuse's extended atmosphere. This companion, now officially named Siwara, appears to be a young F-type star with about 1.6 solar masses. It orbits roughly 4 astronomical units from Betelgeuse's center, which places it between the outer asteroid belt and Jupiter in solar system terms. Here's what makes this remarkable. If Betelgeuse's photosphere extends to about 5.5 astronomical units at maximum, Siwara orbits inside the red supergiant's outer layers. The companion star is literally swimming through Betelgeuse's atmosphere. How does a star survive such an environment? How does its presence affect Betelgeuse's structure and evolution? These questions are only beginning to be explored. The existence of Siwara also affects our understanding of Betelgeuse's size. The companion's orbital motion causes periodic variations in Betelgeuse's observed properties, which previous researchers attributed solely to the red supergiant's pulsations. Separating the companion's effects from Betelgeuse's intrinsic variability requires careful analysis. It's possible that some of what we've interpreted as size changes in Betelgeuse are actually artifacts of the companion's orbit. This complexity, wavelength-dependent measurements, pulsations, convective cells, circumstellar shells, companion stars, illustrates why determining Betelgeuse's size is far from straightforward. We're not measuring a static sphere, but a dynamic, evolving, multi-layered system where the boundary between star and space is fundamentally ambiguous. Yet despite all this uncertainty, one thing remains clear. Betelgeuse is almost incomprehensibly large. Even the most conservative modern estimates place it at over 600 times the Sun's radius. The most generous estimates approach 1,000 solar radii. Either way, we're talking about an object so vast that our familiar solar system analogies barely capture its scale. But size alone doesn't tell the full story. To truly understand Betelgeuse, we need to explore how it reached these dimensions, why it continues to change, and what its massive scale tells us about its ultimate fate. The answers involve stellar evolution, nuclear fusion, and the fundamental forces that govern how stars live and die. And they start with understanding what makes Betelgeuse so dramatically different from our Sun. The difference between Betelgeuse and our Sun isn't just about size. It's about fundamental physics. Our Sun is a main sequence star, steadily fusing hydrogen into helium in its core. This process has continued for nearly 5 billion years and will continue for roughly 5 billion more. The Sun's structure is relatively stable, a dense core surrounded by radiative and convective zones, all held in equilibrium by the balance between gravitational collapse and outward pressure from nuclear fusion. It's a star in its prime, burning fuel at a sustainable rate. Betelgeuse couldn't be more different. Despite being only 10 million years old, a cosmic infant compared to the Sun, it's already approaching the end of its life. That's the cruel mathematics of stellar evolution. The more massive a star, the shorter it lives. Betelgeuse was born with roughly 18 solar masses. That extra mass means far higher core temperatures and pressures, which drives fusion reactions at an exponentially faster rate. Think of it this way. If our Sun is burning fuel like an efficient sedan on a cross-country trip, Betelgeuse is a dragster consuming its entire tank in seconds. The star has already exhausted all the hydrogen in its core and moved on to helium fusion, a process that requires even higher temperatures. Eventually, it'll progress to fusing carbon, then neon, then oxygen, each stage happening faster than the last. But here's where things get truly strange. When Betelgeuse exhausted its hydrogen supply, it didn't simply die. Instead, the core contracted and heated up until helium fusion ignited. The energy released from this process caused the star's outer layers to expand dramatically. Not gradually over billions of years like the Sun's eventual expansion, but rapidly over just a few 100,000 years. This expansion is what transformed Betelgeuse from a massive but relatively compact star into the bloated red supergiant we observe today. When it was on the main sequence, burning hydrogen like the Sun, Betelgeuse would have been perhaps 20 to 40 times the Sun's radius. Large, certainly, but nowhere near its current dimensions. The red supergiant phase changed everything. Why do stars expand when they switch fusion processes? The physics involves something called the mirror principle. When helium fusion begins in the core, it produces more energy than hydrogen fusion did. This increased energy output pushes outward against the star's gravitational pull. Meanwhile, a shell of hydrogen around the core continues fusing, adding even more outward pressure. The outer layers have no choice but to expand outward. As these layers expand, they cool. That's basic thermodynamics. When gas expands, it cools down. Betelgeuse's surface temperature dropped from roughly 10,000 Kelvin to about 3,000 Kelvin. This cooling is what gives the star its distinctive red color. Hot stars are blue or white. Cool stars are red. Betelgeuse, despite its enormous energy output, has a surface cooler than our Sun's. The paradox resolves when you remember that luminosity depends on both temperature and surface area. Betelgeuse's surface is so vast that even at lower temperature, it radiates between 90,000 and 150,000 times more energy than the Sun. It's emitting in 1 second what the Sun produces over several days. This brings us to one of Betelgeuse's most bizarre properties, its density, or rather, its lack of density. Remember that Betelgeuse contains only about 18 solar masses of material spread across a volume that could contain hundreds of thousands of suns. The average density works out to roughly 1/10,000,000th the density of our Sun. To put that in perspective, the Sun's average density is about 1.4 grams per cubic centimeter, slightly denser than water. Betelgeuse's average density is about 1/10,000th of a gram per cubic centimeter. That's far less dense than Earth's atmosphere at sea level. It's less dense than the best laboratory vacuum. In most of Betelgeuse's volume, you could wave your hand and encounter fewer atoms than in the space between Earth and the Moon. The star is essentially a hot, glowing, near vacuum held together solely by its own gravity. This extreme diffuseness has profound implications. First, it means the boundary between Betelgeuse and surrounding space isn't sharp. There's no distinct surface where the star ends and space begins. Instead, density gradually decreases from the relatively dense core outward, through increasingly tenuous layers, until eventually you're in interstellar space without ever crossing a definite edge. Second, the low density means Betelgeuse is constantly losing mass. Stellar winds, streams of particles flowing off the star's surface, carry material away at a prodigious rate. Betelgeuse sheds roughly 1 Earth mass of material every 600 years. That might sound modest, but over the star's lifetime it's lost a significant fraction of its original mass to these winds. The mass loss creates those circumstellar shells we discussed earlier. Material ejected from the star flows outward, cools, and condenses into dust particles. These dust shells can extend for light years around the star, representing different epochs of mass loss throughout Betelgeuse's evolution. When astronomers observe Betelgeuse at infrared wavelengths, they are often seeing thermal emission from this circumstellar dust rather than the star itself. But there's something even stranger about Betelgeuse's structure. The entire star is convective from core to surface. In our Sun, convection occurs only in the outer 30% of the radius. Below that, energy travels outward through radiation, photons bouncing through the dense plasma. But in Betelgeuse, the entire envelope is stirred by massive convective cells. Hot material rises from deep within the star, reaches the surface, cools, and sinks back down in a continuous cycle. These aren't small convection cells like Earth's weather systems. Individual cells can be hundreds of millions of kilometers across, larger than Earth's orbit around the Sun. High-resolution images of Betelgeuse's surface show these cells as bright hotspots where rising material reaches the photosphere. The surface doesn't look like a smooth sphere, but more like a bubbling pot of boiling water, with enormous bubbles constantly forming, breaking, and reforming. This vigorous convection drives much of Betelgeuse's variability. When a massive convective plume reaches the surface, it can temporarily increase the star's brightness and apparent size. When cooler material sinks, the affected region appears dimmer. The Great Dimming of 2019 to 2020 likely resulted from an unusually massive convective upwelling that ejected significant material from the surface. The convective motion also generates powerful magnetic fields. While Betelgeuse's magnetic field strength is still debated, observations suggest localized fields of several Gauss, comparable to Earth's magnetic field, but distributed across a volume billions of times larger. These magnetic fields can channel and accelerate the stellar wind, creating asymmetric outflows that contribute to the star's irregular mass loss pattern. Here's where stellar evolution gets really interesting. Betelgeuse is currently fusing helium in its core, converting it into carbon and oxygen. This process will continue for perhaps another 100,000 years. After that, the core will contract again, heating up until carbon fusion begins, then neon fusion, then oxygen fusion. Each stage produces heavier elements and lasts for progressively shorter periods. The final stage, silicon fusion producing iron, will last only a few days, and then everything changes catastrophically. Iron is special in nuclear physics. Fusing lighter elements into iron releases energy, but fusing iron into heavier elements requires energy input. When Betelgeuse's core becomes iron, fusion will suddenly stop providing outward pressure against gravity. The core will collapse in less than a second, falling inward at speeds approaching 25% of light speed. The collapse will halt when the core reaches nuclear density, when atomic nuclei are packed together as tightly as particles in an atomic nucleus. The infalling material will rebound off this incompressibly dense core, generating a shockwave that tears through the star's outer layers. Within hours, Betelgeuse will explode as a Type II supernova, briefly outshining the entire galaxy. When will this happen? That's the trillion-dollar question. Based on Betelgeuse's current properties, its mass, radius, luminosity, and composition, stellar evolution models suggest the supernova could occur anywhere from tomorrow to 100,000 years from now. The uncertainty stems from how difficult it is to determine exactly where Betelgeuse sits in its evolutionary sequence. Small differences in the star's core composition or rotation rate can shift the explosion timing by tens of thousands of years. Some astronomers argued that the Great Dimming might have been a precursor to imminent explosion. The dramatic mass ejection and surface cooling resembled what models predict for pre-supernova stars. But the star's recovery and return to normal brightness suggested otherwise. Betelgeuse appears stable for now, still comfortably fusing helium. The discovery of Siwaha, the companion star orbiting within Betelgeuse's atmosphere, adds another complication. How does this companion affect Betelgeuse's evolution? Does gravitational interaction with Siwaha influence the convective patterns or mass loss rate? When Betelgeuse eventually explodes, what happens to a companion star orbiting just 4 astronomical units away? These questions remain unanswered, but they highlight why Betelgeuse is so valuable scientifically. This isn't just a big star. It's a laboratory for understanding stellar physics, convection, mass loss, magnetic fields, and supernova progenitors. Everything we learn from Betelgeuse helps us understand how massive stars throughout the universe live, evolve, and die. The size of Betelgeuse, whether it's 700 solar radii or closer to 1,000, ultimately matters less than what that size tells us about the star's nature. This is a dying star in its final evolutionary stages, having exhausted its core hydrogen and expanded into a bloated giant. The enormous radius is a symptom of the star's approaching end, a visible manifestation of the nuclear processes consuming its interior. And that brings us to perhaps the most humbling realization about Betelgeuse. Everything that makes this star extraordinary, its size, its brightness, its turbulent convection, its vigorous mass loss, is temporary. Betelgeuse has existed as a red supergiant for only a few 100,000 years. In another 100,000 years, or perhaps much sooner, it will explode and cease to exist as a star. But what remains after that explosion will be equally extraordinary. The supernova remnant will be spectacular. When Betelgeuse explodes, the shockwave will blast the star's outer layers into space at speeds exceeding 20,000 kilometers per second. This expanding shell of gas, containing all the elements forged during the star's lifetime, plus those created in the explosion itself, will slam into the surrounding interstellar medium, creating a glowing nebula visible across thousands of light years. The Crab Nebula gives us a preview. That supernova remnant, created by a star that exploded in 1054 CE, has been expanding for nearly 1,000 years. Today it spans 11 light-years across, glowing brilliantly in multiple wavelengths, as the shockwave continues heating and ionizing surrounding gas. Betelgeuse's remnant will be similar, but potentially even more dramatic. Given the star's greater mass and the additional material it's already shed into space during its red supergiant phase, those pre-existing shells of ejected material will interact with the supernova blast wave in complex ways. Remember those dust shells extending 4 light-years from Betelgeuse? When the supernova shockwave reaches them, years or decades after the initial explosion, they'll light up like cosmic fireworks, creating expanding rings and shells of glowing gas. The Hubble Space Telescope has captured similar ring structures around supernova 1987A, created when that star's blast wave collided with material ejected thousands of years earlier. But the most exotic remnant will be what's left of Betelgeuse's core. After the core collapse halts at nuclear density, what remains is a neutron star, an object so dense that a sugar cube-sized piece would weigh as much as all of humanity. This stellar corpse will be only about 20 kilometers across, yet contain more mass than our entire sun, compressed to densities where atomic nuclei touch. Neutron stars are laboratories for extreme physics that can't be replicated anywhere else in the universe. Their magnetic fields are trillions of times stronger than Earth's. Their surfaces experience gravity 200 billion times stronger than what we feel. Time itself runs measurably slower near their surfaces due to extreme gravitational time dilation. Atomic matter as we know it cannot exist there. Electrons are crushed into protons, creating a sea of neutrons held together only by quantum degeneracy pressure. Some neutron stars become pulsars, spinning rapidly and beaming radiation from their magnetic poles like cosmic lighthouses. If Betelgeuse's neutron star remnant becomes a pulsar, we might detect its signals from Earth, a rhythmic pulse marking the grave of a once mighty star, spinning perhaps dozens of times per second despite containing more mass than the Sun. There's another possibility. If Betelgeuse's core is massive enough, and this remains uncertain, the collapse might not stop at the neutron star stage. If the core exceeds roughly 3 solar masses, even neutron degeneracy pressure cannot prevent further collapse. The core will shrink past the neutron star stage, past any possible resistance from known physics, until it disappears behind an event horizon. Betelgeuse could leave behind a black hole. This outcome depends critically on how much mass remains in the core after the outer layers are ejected. The supernova explosion will blow away most of Betelgeuse's mass. Perhaps 15 to 18 solar masses worth of material will be scattered into space. But if the core retains more than 3 solar masses, gravitational collapse will continue until space-time itself curves so severely that nothing, Not even light can escape. A stellar mass black hole from Betelgeuse would be roughly 6 to 10 kilometers across at its event horizon, containing perhaps 5 to 10 solar masses. It would be completely invisible except for its gravitational effects and any matter falling into it. Over time, it might accrete material from the surrounding supernova remnant, heating that material to millions of degrees and producing X-rays detectable from Earth. Either outcome, neutron star or black hole, represents matter in its most extreme state, compressed beyond anything possible in ordinary stellar interiors. These objects push against the fundamental limits of physics, existing at densities where our understanding of matter, energy, space, and time becomes uncertain. But we're getting ahead of ourselves. These futures, supernova, neutron star, black hole, remain hypothetical until the explosion actually occurs. And that brings us back to the question everyone wants answered. When will Betelgeuse explode? The honest answer frustrates both astronomers and the public. We don't know. Could be tomorrow. Could be 100,000 years from now. The uncertainty stems from how difficult it is to determine exactly where Betelgeuse sits in its evolutionary sequence. Stellar evolution models can predict general timelines. A star of Betelgeuse's mass should spend roughly 10 million years as a main sequence star, fusing hydrogen. Then perhaps 100,000 years as a red supergiant, fusing progressively heavier elements. But the exact timing depends on details we cannot directly observe. The composition and structure of the core, the star's rotation rate, its magnetic field strength, how much mass it's losing through stellar winds. Small differences in these parameters can shift the explosion timing by tens of thousands of years. A star rotating faster burns through its fuel more quickly. A star with slightly lower metallicity evolves differently. A star losing mass at a higher rate might delay core collapse by removing outer layers that would otherwise contribute pressure. These variables combine in complex, non-linear ways that make precise predictions impossible. The Great Dimming seemed to offer a clue. When Betelgeuse dimmed dramatically in 2019 to 2020, some astronomers wondered whether this might be a precursor to imminent explosion. Pre-supernova stars are expected to undergo dramatic changes, increased mass loss, surface instabilities, brightness variations. The Titanic eruption that ejected moon masses of material certainly qualified as dramatic. But Betelgeuse recovered. The star returned to normal brightness, resumed its regular pulsations, and showed no other signs of imminent explosion. The dimming event, remarkable as it was, appears to have been a violent surface phenomenon rather than a core instability. The engine driving Betelgeuse, helium fusion in its core, continues operating normally. This tells us something important. Betelgeuse is comfortably burning helium, probably for tens of thousands of years more. The star hasn't entered the final rapid stages of neon, oxygen, and silicon fusion. Those stages will be much shorter, years, months, days, and likely accompanied by detectable changes in the star's behavior. When Betelgeuse approaches true explosion readiness, we might see neutrino emissions increase dramatically as the core temperature rises. We might observe more frequent and violent surface eruptions. The star's brightness might become increasingly erratic. But for now, Betelgeuse appears stable. The star is dying, yes, but death will not come immediately. This uncertainty about timing doesn't diminish Betelgeuse's scientific value. Every observation teaches us something about stellar physics, convection, mass loss, and supernova progenitors. The star serves as a natural laboratory for phenomena we cannot create in any terrestrial facility. Magnetic fields threading through plasma at kilogauss strengths, convective cells larger than Earth's orbit, shock waves propagating through tenuous atmospheres, dust formation in stellar winds, the discovery of Siwara, the companion star orbiting within Betelgeuse's extended atmosphere, opened entirely new questions. How did this companion form? Did it condense from material ejected by Betelgeuse, or was it captured gravitationally? How does it survive in an environment where temperatures reach thousands of degrees and radiation pressure should tear away any atmosphere? And what happens when Betelgeuse explodes with Siwara still orbiting just 4 astronomical units away? The companion will be vaporized, obviously. The supernova shockwave will hit Siwara with unimaginable violence, heating the smaller star to millions of degrees in seconds. Any remaining atmosphere will be stripped away. The star itself might be completely disrupted, torn apart by the blast. Or perhaps it will survive as a stripped stellar core, flung outward at tremendous velocity, a hypervelocity star ejected from the system by the supernova's asymmetric explosion. Binary interactions before supernova can produce some of the most exotic outcomes in astrophysics. If Siwara is eventually engulfed by Betelgeuse's expanding envelope, the companion might spiral inward through friction, potentially merging with the supergiant. This could trigger instabilities that accelerate the explosion timeline. Alternatively, the merger might inject additional angular momentum into Betelgeuse's core, affecting how the star collapses and what kind of remnant forms. Some of the universe's most energetic phenomena, gamma-ray bursts, magnetars, X-ray binaries, result from binary star interactions during supernova. While Betelgeuse's supernova will likely be a standard Type II core collapse event, the presence of Siwara introduces possibilities for more exotic outcomes. But these remain speculations built on speculations. We know so little about Siwara. Its true mass, composition, orbital parameters remain uncertain. We don't know if it will survive until Betelgeuse explodes or be consumed earlier. We don't even know for certain that Siwara exists. The detection remains tentative, requiring confirmation from additional observations. What we do know is that Betelgeuse's size makes all of this possible. A smaller star couldn't support a companion orbiting within its atmosphere. A less massive star wouldn't produce the vigorous convection and mass loss that created the extended circumstellar environment. A cooler star wouldn't generate the radiation pressure driving stellar winds. Everything remarkable about Betelgeuse, its variability, its asymmetry, its violent surface phenomena, connects directly to its enormous size. That size represents a temporary condition, a brief phase in stellar evolution. Betelgeuse has been a red supergiant for perhaps a few 100,000 years. In another 100,000 years, or possibly much sooner, it will explode. The red supergiant phase, despite producing the most visually dramatic stars in the universe, represents only about 1% of a massive star's lifetime. Most of Betelgeuse's existence was spent as a hot, blue, much smaller main sequence star. For roughly 10 million years, Betelgeuse was similar to Rigel, brilliant, blue-white, perhaps 40,000 degrees at its surface, no more than 30 or 40 solar radii across. That earlier incarnation fused hydrogen steadily, maintained hydrostatic equilibrium, and showed none of the dramatic variability we see today. The transition from main sequence star to red supergiant happened relatively quickly in astronomical terms. As core hydrogen exhausted, the core contracted and heated, while the envelope expanded and cooled. Over perhaps just a few thousand years, Betelgeuse transformed from a compact blue star to the bloated red giant we observe today. That transformation wasn't gradual decline, it was catastrophic restructuring. The core, no longer supported by hydrogen fusion, collapsed inward under its own gravity. Temperature and pressure skyrocketed, helium ignition began, and the star's envelope, suddenly receiving vastly increased energy from the contracting core, expanded outward like a balloon inflating in seconds. The outer layers cooled as they spread across increasingly vast distances. Surface temperature dropped from 40,000 degrees to barely 3,000. The star's color shifted from blue-white to deep red, and Betelgeuse became the supergiant we observe today. But here's what makes this transformation truly extraordinary. The physics driving it operates on scales that demolish our everyday intuitions about matter and energy. Core helium fusion releases energy through a completely different process than hydrogen fusion. 4 helium nuclei combine to form carbon, releasing less energy per reaction than hydrogen fusion, but doing so at temperatures exceeding 100 million degrees Kelvin. The core contracts to densities where matter exists in states impossible to recreate in terrestrial laboratories. And the envelope expands to densities lower than the best vacuum chambers on Earth. This creates a star with no clear boundary. Where exactly does Betelgeuse end and space begin? The photosphere, that layer where photons finally escape after countless scatterings, sits roughly 764 solar radii from the center. But above the photosphere lies the chromosphere, an irregular layer of hot gas extending perhaps another 100 solar radii outward. Above that, the corona, even hotter but far more tenuous, extends another few hundred radii. And beyond the corona, stellar wind material flows outward continuously, creating a circumstellar envelope that extends trillions of kilometers from the star. Measuring this envelope revealed just how much mass Betelgeuse continuously sheds into space. The outer edge extends well over 1 trillion kilometers from the star's center. Light from Betelgeuse takes roughly 2 months just to traverse the gas shell surrounding it. That's not light traveling from Betelgeuse to Earth. That's light escaping Betelgeuse's own atmosphere. The star exists within a vast cocoon of its own shed material, gas and dust blown outward by radiation pressure and stellar winds. Images from the Very Large Telescope Interferometer in 2009 showed enormous plumes of gas extending 30 astronomical units from the star. 30 astronomical units. That's the distance from the Sun to Neptune. These weren't small atmospheric features, but titanic eruptions comparable to the entire outer solar system. The mass ejection captured in those images equaled the distance between our Sun and its most distant major planet, all ejected from a single stellar outburst. And those plumes represent just one episode of mass loss. Betelgeuse continuously sheds material through normal stellar winds, losing perhaps 1 solar mass every 100,000 years. But occasionally, violent surface events eject vastly more material in single catastrophic eruptions. The Great Dimming of 2019 through 2020 demonstrated this dramatically. Betelgeuse ejected 400 billion times as much mass as a typical coronal mass ejection from our Sun. The chunk blown into space likely weighed several times the mass of Earth's moon, and that material, once ejected, cooled and condensed into dust that temporarily obscured the star from our view. This violent mass loss creates multiple shells of material surrounding Betelgeuse at various distances. Observations reveal at least 3 distinct dust shells extending up to 4 light-years from the star. 4 light-years. That's roughly the distance to the nearest star beyond our Sun. The inner shell extends from about 1.5 to 4 arcseconds from Betelgeuse. The outer shell reaches as far as 7 arcseconds. Converting these angular measurements to physical distances requires assumptions about the star's true size. But even conservative estimates suggest the inner shell extends 50 to 150 stellar radii from the photosphere. The outer shell reaches 250 stellar radii or more, over 1,000 astronomical units from the star's center. Each shell represents a different episode in Betelgeuse's mass loss history. Material ejected 10,000 years ago now drifts through space hundreds of astronomical units from the star. Material ejected 1,000 years ago forms an intermediate shell. Recently ejected material creates the innermost shell, and between these discrete shells, continuous stellar wind material fills the space, creating a complex, layered structure that extends far beyond anything we'd normally consider part of the star itself. This raises a fundamental question about stellar size. When we say Betelgeuse has a radius of 764 solar radii, we're referring specifically to the photosphere. But is that really the star's size? The chromosphere extends beyond that. The corona extends even further. The circumstellar envelope extends dramatically further still, and the shells of ejected material extend to distances measured in light years. Which of these represents Betelgeuse's true boundary? The answer depends entirely on what wavelength you're observing at. Look at Betelgeuse in visible light, and you see primarily the photosphere. The star appears roughly 56 milliarcseconds across, corresponding to that 764 solar radius figure. But observe in near-infrared wavelengths, and you're seeing deeper into the atmosphere, closer to the region where energy generation actually occurs. The star appears slightly smaller, perhaps 54 milliarcseconds. Observe in mid-infrared, and you're detecting emission from warm dust in the inner circumstellar shell. The star appears larger, potentially 60 milliarcseconds or more. Observe in radio wavelengths, and you're seeing emission from ionized gas in the outer envelope. The star appears larger still, perhaps hundreds of milliarcseconds. This wavelength dependence isn't measurement error. It reflects the genuine multi-layered structure of Betelgeuse's extended atmosphere. The star doesn't have a single size. It has many sizes depending on which physical region you're measuring. The photosphere sits at one radius. The temperature minimum, where the atmosphere reaches its coolest point before the chromosphere begins, sits at another radius. The chromosphere itself spans a range of radii. The base of the corona sits at yet another radius, and the outer boundary of the circumstellar envelope sits at radii measured in astronomical units rather than solar radii. This complexity means that comparing Betelgeuse to other supergiant stars requires careful specification of exactly what's being compared. Mu Cephei, another red supergiant, has an estimated radius between 972 and 1420 solar radii, significantly larger than Betelgeuse by most estimates. VY Canis Majoris, one of the largest known stars, may reach 1420 solar radii. UY Scuti, often cited as one of the largest stars, has an estimated radius around 909 solar radii. These figures all refer to photospheric radii, the most commonly cited size metric. But photospheric radius captures only part of the story. Betelgeuse's circumstellar envelope may extend further than those of larger stars. Its mass loss rate might be higher. Its shells of ejected material might reach greater distances. And its proximity to Earth combined with its brightness allows far more detailed observations than more distant supergiants. We can resolve features on Betelgeuse's surface that remain impossible to detect on stars like VY Canis Majoris or UY Scuti. We can track variability over timescales from days to decades. We can observe mass ejection events as they happen. We can map the structure of circumstellar shells in 3 dimensions. This observational advantage makes Betelgeuse arguably the most important supergiant for understanding stellar physics. Not the largest, not the most luminous, but the most accessible to detailed study. Every observation reveals new complexity. Every new instrument uncovers previously hidden structures. And every discovery raises new questions about how such enormous, dynamic, violently active stars actually work. Consider the convective structure. Observations reveal giant cells of rising and sinking gas, each cell potentially as large as a small star. These aren't small-scale turbulence like convection in Earth's atmosphere. These are coherent structures hundreds of millions of kilometers across, rising from the stellar interior to the surface over timescales of months to years. Hot material rises, reaches the surface, cools through radiation, then sinks back down to be reheated. This convection drives many of Betelgeuse's observable properties. The variability in brightness results partially from convective cells bringing hot material to the surface or allowing cool material to dominate. The asymmetric appearance results from different regions of the surface being dominated by rising or sinking material. The mass loss may be enhanced by convective energy driving material beyond the star's gravitational binding. Even the star's rotation, surprisingly slow for such a young massive star, might be affected by convective drag redistributing angular momentum throughout the envelope. But here's what really captures the imagination. These convective cells make Betelgeuse fundamentally different from smaller stars. Our Sun has convection, certainly. The outer 30% of the Sun's radius undergoes convective heat transport. But solar convection cells are relatively small, ranging from supergranules a few hundred kilometers across to smaller granules just 1,000 kilometers wide. The largest convective structures in the Sun represent a tiny fraction of the solar radius. Betelgeuse's convective cells can span significant fractions of the stellar diameter. A cell 100 million kilometers across represents roughly 15% of Betelgeuse's diameter. When such a cell reaches the surface, it creates a hotspot, visible in interferometric observations, a region thousands of degrees hotter than surrounding areas. When it sinks, that region dims and cools. The star's surface becomes a constantly shifting mosaic of hot and cool regions, rising and sinking cells, ejected material, and infalling gas. This turbulent surface drives the mass loss that creates Betelgeuse's extended circumstellar environment. Convective energy helps lift material above the photosphere. Radiation pressure from the star's enormous luminosity pushes that material outward. Stellar winds, driven by complex interactions between radiation, gas pressure, and magnetic fields accelerate the material to escape velocity, and periodic ejections, possibly triggered by particularly violent convective eruptions, blow vast quantities of material into space in single catastrophic events. The mass loss itself occurs at staggering rates. Betelgeuse sheds material equivalent to Earth's entire mass roughly every 400,000 years. That might sound gradual until you realize we're talking about an entire planet's worth of matter being ejected into space over timescales astronomically brief. The stellar wind alone carries away approximately 1/10,000,000th of a solar mass per year, a rate that would empty a star like our Sun in 10 million years. But Betelgeuse isn't gradually depleting through this mass loss. The star generates energy internally far faster than it loses material externally. The mass loss represents a consequence of the star's enormous size and luminosity, not a threat to its immediate survival. The ejected material doesn't simply disappear into the void. It creates an extended circumstellar environment that, depending on definition, might be considered part of the star itself. The immediate circumstellar envelope, the region closest to the photosphere, extends several stellar radii outward. This region contains gas still hot enough to emit thermal radiation, material recently ejected but not yet cooled to ambient interstellar temperatures. Beyond that lies a transition zone where gas cools rapidly, forming molecules and eventually dust particles. And further still, multiple shells of older ejected material expand outward at various speeds, each shell representing a different era in Betelgeuse's recent evolutionary history. Some shells extend remarkable distances. Observations reveal dust shells extending 4 light-years from the star, material ejected thousands of years ago now traveling through interstellar space at tens of kilometers per second. These shells contain elements synthesized in Betelgeuse's interior, then transported to the surface through convection and ejected through winds and explosive events. Carbon, nitrogen, oxygen, heavier elements up through iron, all products of stellar nucleosynthesis now spreading through space, eventually to be incorporated into future generations of stars and planets. The Great Dimming event of late 2019 and early 2020 provided unprecedented insight into these mass ejection processes. Betelgeuse's brightness dropped dramatically over several months, reaching its faintest level in recorded history before recovering equally dramatically. Initial speculation ran wild. Was the star beginning its collapse towards supernova? Had something catastrophic occurred in the stellar interior? The truth proved equally fascinating, though less immediately apocalyptic. The observations revealed that Betelgeuse had ejected a massive chunk of its photosphere in a violent eruption. The ejection involved material equivalent to several lunar masses blown off the star's surface in a single catastrophic event. This represented 400 billion times the mass typically ejected during solar coronal mass ejections, scaled up to stellar proportions. The ejected material, initially hot and ionized, cooled rapidly as it expanded away from the star. And as it cooled, some of that gas condensed into dust particles. Those dust particles, tiny solid grains formed from material that moments before had been part of a stellar atmosphere, created an obscuring cloud between Betelgeuse and Earth. The star itself continued shining at normal brightness. But from our perspective, a dust cloud partially blocked the starlight, causing the apparent dimming. As months passed and the dust cloud dispersed, gradually moving out of our line of sight, Betelgeuse's brightness recovered to normal levels. This event demonstrated several crucial facts about Betelgeuse's nature. First, the star undergoes violent surface eruptions, far more extreme than anything occurring on the Sun. Second, these eruptions can eject significant fractions of the stellar photosphere, temporarily leaving behind cooler surface regions. Third, the ejected material can rapidly form dust, creating circumstellar clouds that affect observations. And fourth, these events occur on human timescales, observable and documentable with modern instruments. The eruption likely originated from convective processes deep in the stellar interior. A particularly massive convective cell, perhaps 100 million kilometers across, rose from the interior carrying enormous thermal energy. When this cell reached the surface, the energy release created shocks and pressure waves that literally blew away a portion of the photosphere. The affected region, now exposed and cooler than surrounding areas, created the observed temperature asymmetry. And the ejected material, cooling and forming dust, created the obscuring cloud. Understanding these mass ejection events requires grasping the enormous energies involved. The kinetic energy in several lunar masses of material, moving at tens of kilometers per second, exceeds anything achievable through human technology by factors of trillions. The radiation energy driving these winds and eruptions represents the star's luminosity, 14,000 times the Sun's energy output, focused through a photosphere with temperatures and densities that would vaporize any known material instantly. The magnetic fields threading through the stellar atmosphere, while poorly understood, might carry enough energy to power entire planetary systems. All this activity, this constant churning and ejection and pulsation, makes defining Betelgeuse's size remarkably complex. When we say the star has a radius of 764 solar radii, we're referring specifically to the photosphere at a particular wavelength at a particular time in the pulsation cycle. Add the immediate circumstellar envelope and the effective radius increases by tens of percent. Include the dust-forming region and it grows larger still. Count the extended shells of previously ejected material and the size becomes multiple light years, encompassing volumes thousands of times larger than the photosphere alone. Each definition serves different purposes. For understanding the star's energy output and temperature, the photospheric radius matters most. For modeling mass loss and stellar evolution, the extent of the circumstellar envelope becomes crucial. For studying dust formation and the chemical enrichment of the interstellar medium, the outer shells demand attention. There's no single right answer to how big is Betelgeuse, only different measurements appropriate for different questions. The star's variability adds further complexity. Betelgeuse pulsates with multiple periods, the dominant cycle lasting approximately 400 days. During each pulsation, the star's radius changes by roughly 60%. 60%, that's not a subtle variation. That's the difference between a star 500 solar radii in diameter and one 800 solar radii across, a range larger than the distance from Earth to the Sun. The star physically swells and contracts like a beating heart, its surface moving outward and inward at speeds of several kilometers per second. This pulsation connects directly to the convective dynamics. As convective cells rise and fall, they transport energy that drives the oscillations. The pulsations aren't simple sine waves, but complex patterns involving multiple overlapping periods. Different regions of the stellar surface might be expanding while others contract. Hotspots created by rising convection might brighten one area, while cool spots dim another. The combination creates a dynamic, ever-changing star that never looks exactly the same twice. Longer-term changes add yet another layer. Between 1993 and 2009, Betelgeuse's measured angular size decreased by 15%, a shrinkage of nearly 0.9 astronomical units over 15 years. Whether this represented actual physical contraction or changes in atmospheric structure remains debated. The star might have undergone a sustained period of reduced radius, or atmospheric conditions might have changed, altering which layers of the star dominated observations at particular wavelengths. Or the measurement techniques themselves might have systematic differences that created apparent shrinkage where none actually occurred. Recent refined measurements suggest Betelgeuse might be smaller than many previous estimates indicated. The 2020 study, using multiple independent techniques, converged on a radius near 764 solar radii, notably smaller than estimates exceeding 1,000 solar radii from earlier work. This revision doesn't mean previous researchers made errors. It reflects improved observational capabilities, better modeling techniques, and more sophisticated understanding of how to interpret measurements of such complex objects. Each generation of astronomers refines the previous generation's work, gradually approaching ever more accurate descriptions of reality. What makes these refinements crucial extends beyond mere academic precision. Betelgeuse's size directly relates to its evolutionary state, which determines when the star will explode as a supernova. Larger radius generally indicates more advanced evolution, suggesting shorter remaining lifetime. The revised smaller radius implies Betelgeuse might have more time left than previously thought, perhaps tens of thousands of years, rather than the immediate-term predictions that periodically circulate in popular media. But tens of thousands of years remains astronomically brief. Betelgeuse formed roughly 10 million years ago. For 9 million years it burned hydrogen in its core, shining as a bright but otherwise unremarkable massive star. Then, having exhausted its core hydrogen, it began the helium-burning phase that inflated it into the supergiant we observe today. This phase has lasted perhaps 1 million years at most. The next phases, burning progressively heavier elements through carbon, neon, oxygen, and finally silicon, will proceed ever faster. Carbon burning takes thousands of years, neon burning takes years, oxygen burning takes months, silicon burning, the final stage before core collapse, takes days. Once silicon burning begins, Betelgeuse's fate is sealed. The core will produce iron, an element that cannot be fused to release energy. With no energy source remaining, the core will collapse catastrophically, rebounding in a supernova explosion that will briefly outshine the entire galaxy. The star's outer layers, including all that material we've been discussing, will be blown into space at a significant fraction of light speed, and where Betelgeuse once shone, only a neutron star, or possibly a black hole, will remain. When might this occur? The honest answer, we don't know precisely. Could be tomorrow, could be 100,000 years from now. The refined size measurements help narrow the possibilities, but cannot provide certainty because we cannot observe Betelgeuse's core directly. We see only surface phenomena, effects that propagate outward from interior processes we must infer rather than measure. The core might be burning helium steadily, indicating millennia of remaining lifetime, or it might have already progressed to carbon burning, suggesting centuries. We simply cannot tell from surface observations alone. What we can say with confidence, Betelgeuse will explode within an astronomical eye blink. Whether that eye blink spans decades or spans millennia matters little on cosmic timescales. The star stands as a monument to stellar gigantism, to the strange physics of extremely massive stars, to the violent processes that forge heavy elements and distribute them through space. Its enormous size, its turbulent dynamics, its prodigious mass loss, all represent natural consequences of being a star 15 to 20 times more massive than the Sun. Massive stars don't simply exist in space. They fundamentally alter it. Betelgeuse demonstrates this principle through consequences extending far beyond its visible boundaries. The star sheds material constantly, not through catastrophic events like the Great Dimming, but through ordinary stellar winds that strip away its outer layers at rates incomprehensible by terrestrial standards. Every year, Betelgeuse loses mass equivalent to Earth's entire mass. Not once in its lifetime, annually. This relentless hemorrhaging of material creates something far larger than the photosphere itself, a vast circumstellar environment that dwarfs even Betelgeuse's enormous physical body. The outer edge of this circumstellar envelope extends over 1 trillion kilometers from the star. Light traveling at 300,000 kilometers per second requires 2 months to escape this gas shell. 2 months, not 2 seconds or 2 minutes. The distance from Earth to Sun, 1 astronomical unit, light crosses in 8 minutes. Betelgeuse's circumstellar envelope extends thousands of astronomical units, creating a region where starlight itself becomes imprisoned, scattered and absorbed by the very material the star shed centuries or millennia ago. This extended structure reveals itself through observations at different wavelengths. Images from the Very Large Telescope Interferometer in 2009 showed massive gas plumes extending 30 astronomical units from Betelgeuse into surrounding space. For reference, 30 astronomical units equals the distance between our Sun and Neptune, the outermost major planet. Betelgeuse casually ejects material across distances encompassing our entire planetary system. These plumes represent convective upwellings so powerful they breach the star's gravitational grip, carrying hot gas into the surrounding void where it cools, condenses, and forms dust. Multiple concentric shells surround Betelgeuse at various distances, each recording a different epoch of mass loss. Studies identify at least 3 distinct dust shells extending 4 light-years from one hemisphere of the dying star. 4 light-years. The nearest star to our Sun sits just over 4 light-years distant. Betelgeuse's influence extends across distances comparable to interstellar separations, filling a volume of space that makes its already enormous photosphere seem almost modest by comparison. The innermost shell extends from roughly 50 to 150 stellar radii, translating to 300 to 800 astronomical units. Already this exceeds the size of our solar system many times over. The middle shell extends further still. The outermost shell reaches approximately 250 stellar radii, roughly 1,400 astronomical units from the star's center. At this distance, Betelgeuse's light takes nearly 3 days to arrive. The Sun's light, reaches Earth in 8 minutes. Betelgeuse's influence propagates outward for 3 days before reaching the inner edge of its outermost dust shell. These shells don't represent continuous material, but rather discrete episodes of enhanced mass loss separated by time. Perhaps 10,000 years ago, Betelgeuse experienced a period of particularly vigorous convection or pulsation. Material ejected during that epoch now forms the outermost shell, expanding steadily into interstellar space. 5,000 years later, another episode created the middle shell. More recently, within the past few millennia, the innermost shell formed. Each shell carries information about Betelgeuse's state when that material was ejected, creating an archaeological record written in gas and dust rather than stone and pottery. The composition of this circumstellar material matters tremendously. Betelgeuse manufactures heavy elements through fusion in its core, then dredges them to the surface through convection, finally expelling them into space through stellar winds and occasional violent eruptions. Carbon, nitrogen, oxygen, silicon, iron, elements forged through nuclear fusion now drift through space, eventually contributing to future generations of stars and planets. Betelgeuse isn't simply large. It's actively enriching the interstellar medium with material that didn't exist when the universe began. Understanding this extended environment requires grappling with the star's internal structure. Betelgeuse is not a uniform sphere of hot gas. Rather than a single smooth surface, the star resembles a boiling cauldron, where enormous convective cells, each potentially larger than Earth's entire orbit, carry heat from interior to surface. These cells create a mottled, irregular appearance entirely different from the smooth photosphere of stars like our Sun. Interferometric observations reveal hotspots on Betelgeuse's surface, bright regions thought to mark locations where convective upwellings bring particularly hot material to the surface. These hotspots aren't small features. They span significant fractions of the stellar diameter, regions large enough to encompass our entire inner solar system. As hot material reaches the surface, it radiates energy, cools, then sinks back into the interior, completing the convective cycle. This process occurs continuously across Betelgeuse's entire photosphere, creating a dynamic, turbulent surface unlike anything in our immediate solar neighborhood. Unlike the Sun, where convection occurs only in an outer envelope, while the interior remains radiative, Betelgeuse's entire envelope appears convective. From the helium-burning core outward through hundreds of solar radii, heat transport occurs primarily through bulk motion of gas rather than photon diffusion. This fundamental difference in structure explains many of Betelgeuse's peculiar properties: its variability, its asymmetric appearance, its prodigious mass loss, its extended atmosphere. Convection drives everything. The violence of this convection occasionally produces spectacular results. The Great Dimming of 2019 to 2020 likely originated when a convective plume over 1 million kilometers across reached the surface with unusual intensity. This upwelling ejected a chunk of photosphere outward with such force that it escaped Betelgeuse's gravity entirely, cooling rapidly as it expanded into surrounding space. Within weeks, the ejected material had cooled sufficiently to form dust, creating a cloud that partially obscured the star from Earth's perspective. The event demonstrated that Betelgeuse can experience surface mass ejections, dwarfing anything seen on the Sun. The ejected mass weighed several times more than Earth's moon. 400 billion times the mass of a typical solar coronal mass ejection. Not a factor of 10 or 100. 400 billion. These dynamics make defining Betelgeuse's size surprisingly ambiguous. The photosphere, the layer where optical light escapes, extends to roughly 764 solar radii. But above the photosphere lies a chromosphere, a region of lower density gas heated by shocks and magnetic activity. Above that, an extended atmosphere merges gradually into the circumstellar envelope. Where exactly does Betelgeuse end and space begin? No sharp boundary exists. Density decreases smoothly from the photosphere outward through the chromosphere, an extended atmosphere, until eventually becoming indistinguishable from the surrounding interstellar medium. This gradual transition means measurements at different wavelengths produce different size estimates. Visible light escapes primarily from the photosphere, yielding the standard radius near 764 solar radii. Near-infrared observations penetrate deeper, seeing through the photosphere to hotter layers beneath, producing smaller radius estimates. Mid-infrared observations detect warm dust in the circumstellar envelope, yielding much larger apparent sizes. Radio observations see even further out, detecting molecular gas in shells far removed from the star itself. Each wavelength reveals a different layer of this complex multi-component system. Recent discoveries add yet another layer of complexity. In 2025, astronomers announced evidence for a stellar companion orbiting within Betelgeuse's extended atmosphere. This companion, designated Siwara, possesses 1.6 solar masses, making it significantly more massive than initially expected for objects in such an environment. Siwara appears to be a young F-type star, hotter and smaller than Betelgeuse, but substantial in its own right. The companion orbits 4 astronomical units from Betelgeuse's center. 4 astronomical units. In our solar system, this distance falls between the asteroid belt's outer edge and Jupiter's orbit. Siwara orbits well within Betelgeuse's photosphere, assuming the supergiant reaches its maximum estimated size. How does a star survive inside another star? The answer lies in Betelgeuse's extraordinarily low density. The photosphere's outermost regions are more tenuous than any vacuum achievable in terrestrial laboratories. Siwara doesn't experience Betelgeuse's photosphere as a solid barrier, but rather as thin gas through which it moves relatively freely. This arrangement won't last. Models suggest Siwara will spiral inward, eventually merging with Betelgeuse within 10,000 years. The merger might trigger dramatic events, potentially affecting when and how Betelgeuse explodes. Or it might pass relatively quietly, Siwara's mass simply adding to Betelgeuse's own. We don't know because we've never observed such a merger. Siwara's presence raises questions about Betelgeuse's history. Did the 2 stars form together? Or did Betelgeuse capture Siwara more recently? The companion's youth suggests it formed relatively recently, perhaps from material in Betelgeuse's circumstellar disk. Or perhaps Siwara is older than it appears, its surface rejuvenated by accreting material from Betelgeuse's stellar wind. These complexities illustrate why answering how big is Betelgeuse requires more than a single number. The photosphere extends 764 solar radii. The chromosphere extends further. The extended atmosphere reaches beyond that. The circumstellar envelope spans thousands of astronomical units. Dust shells extend light years, and a companion star, orbits within the photosphere itself. Betelgeuse is not simply a star, but an entire system, a complex, dynamic, evolving structure that defies simple description. This complexity also explains why size estimates have changed so dramatically over time. Early measurements captured some aspects of the system while missing others. As observational techniques improved, new layers of structure revealed themselves, each requiring interpretation and integration into existing models. The current best estimate of 764 solar radii represents the photospheric radius measured at specific wavelengths using specific techniques. Other measurements at other wavelengths will yield different values, not because either is wrong, but because they measure different physical structures. Understanding Betelgeuse's size ultimately requires understanding the star as a dynamic, multi-layered system constantly interacting with its environment. Material flows outward through stellar winds. Convection churns the interior. Pulsations expand and contract the photosphere. Companion stars orbit through the extended atmosphere. Dust shells mark ancient mass loss events. Each component contributes to the whole, creating a structure whose true scale extends far beyond what we might initially imagine when we simply ask about the star's size. The question everyone wants answered is when. When will Betelgeuse explode? When will this cosmic giant finally collapse under its own exhausted core and detonate in one of the universe's most spectacular displays of stellar death? The answer frustrates and fascinates in equal measure, because determining the exact timing of a supernova is one of astronomy's most challenging problems. At roughly 10 million years old, Betelgeuse has lived fast and will die young. Our Sun, by comparison, has existed for nearly 5 billion years and will continue burning for another 5 billion before exhausting its fuel. But Betelgeuse compressed its entire main sequence lifetime into a mere fraction of that duration, racing through hydrogen fusion at a prodigious rate. The star has already exhausted the hydrogen in its core and is now fusing helium into heavier elements. Current observations indicate Betelgeuse is burning helium in its core, which means it's nowhere near exploding. We could be looking at around 100,000 years before an explosion happens. 100,000 years sounds like an immense timescale from human perspective, spanning the entire history of modern human civilization many times over. Yet astronomers describe this as imminent on cosmic timescales because it represents less than 1% of the star's total lifetime. The uncertainty stems from incomplete understanding of stellar evolution at this critical phase. What happens inside a star as it approaches core collapse remains partly theoretical, based on computer models that must account for nuclear physics, hydrodynamics, convection, rotation, magnetic fields, and mass loss simultaneously. Small changes in initial assumptions about mass or composition can shift predicted timelines by tens of thousands of years. Some models suggest Betelgeuse might be closer to explosion than we think, perhaps within 10,000 years. Others extend the timeline to several 100,000 years. The Great Dimming event of late Tabi Tau, 0019, initially sparked speculation that Betelgeuse might be entering its final death throes. The star dimmed to its faintest observed magnitude in modern times, dropping to magnitude 1.6 by early 2020. Social media erupted with predictions of imminent supernova. Astronomers received countless inquiries about whether the explosion had already occurred, and we were simply waiting for the light to reach us. but subsequent analysis revealed the dimming resulted from a massive ejection of material that cooled and formed a dust cloud, temporarily obscuring the star. Betelgeuse blew 400 billion times as much mass as is usually emitted during a coronal mass ejection, and the chunk it spewed out into space likely weighed several times as much as our Moon. This titanic eruption was caused by a convective plume more than 1 million kilometers in diameter that bubbled up from deep within the star, producing shocks and pulses that ejected a chunk of photosphere. The ejected material cooled and formed a dust cloud that partially blocked light from the star. By mid-2020, Betelgeuse had returned to normal brightness, its temporary veil of dust dissipating into space. The event provided unprecedented insights into mass loss mechanisms, but did not indicate imminent core collapse. Nevertheless, such violent surface eruptions demonstrate the increasingly unstable nature of Betelgeuse's outer layers as the star approaches the end of its evolution. Understanding what will happen when Betelgeuse finally does explode requires examining the physics of core collapse supernovae. Deep in the star's center, nuclear fusion is creating progressively heavier elements. Hydrogen fused into helium during the main sequence phase. Now helium fuses into carbon and oxygen. Eventually carbon will fuse into neon and magnesium, neon into oxygen and magnesium, oxygen into silicon and sulfur, and finally silicon into iron. Each successive fusion stage releases less energy and occurs more rapidly. Helium burning might continue for hundreds of thousands of years. Carbon burning lasts perhaps 1,000 years. Oxygen burning takes about a year. Silicon burning, the final stage, completes in just days. The end comes when the core fills with iron. Iron represents the most stable atomic nucleus, the bottom of the nuclear binding energy curve. Fusing iron requires energy input rather than releasing energy. When the core becomes predominantly iron, fusion stops. The star's internal structure at this point resembles an onion, with concentric shells of different elements surrounding the iron core. Overlying the iron are shells of silicon, oxygen, neon, carbon, helium, and finally, the hydrogen-rich envelope. The iron core continues to grow as silicon burning in the surrounding shell adds more material. When the core reaches approximately 1.4 solar masses, a critical threshold known as the Chandrasekhar limit, it can no longer support itself against gravitational collapse. Electron degeneracy pressure, the quantum mechanical effect that had been holding up the core, fails catastrophically. What happens next occurs almost too quickly to comprehend. The core collapses from roughly the size of Earth to a sphere perhaps 20 kilometers across in less than 1 second. Protons and electrons merge into neutrons, releasing vast quantities of neutrinos. The outer layers of the star, suddenly unsupported, begin falling inward at significant fractions of light speed. When the infalling material hits the incompressible neutron core, it rebounds in a shock wave that propagates outward through the star. This shock wave, carrying energy equivalent to the sun's entire 10 billion year lifetime, released in seconds, blows the star apart. From Earth's perspective, we would see Betelgeuse suddenly brighten to magnitude -12 or brighter, rivaling the full moon in apparent brightness. The supernova would be visible during daylight for weeks, easily bright enough to read by at night. The spectacle would persist for months as the expanding debris cloud glowed from radioactive decay of nickel and cobalt isotopes created in the explosion. Neutrinos from the core collapse would arrive first, traveling at light speed and passing through Earth largely undetected except by specialized detectors deep underground. The light from the explosion would arrive roughly 8 minutes later, delayed by the time required for the shockwave to propagate through the star's extended atmosphere. Observatories worldwide would pivot to observe this once-in-a-civilization event, capturing data across the electromagnetic spectrum. Scientists would gain unprecedented insights into supernova physics, element formation, shockwave dynamics, and the final moments of massive stars. The explosion would create and disperse heavy elements throughout the interstellar medium. Every atom of gold, platinum, uranium, and other elements heavier than iron in the universe, formed in supernovae or neutron star mergers. Betelgeuse's supernova would enrich the surrounding region with these elements, potentially triggering new star formation in the compressed gas clouds. But there's a catch to all of this. Because Betelgeuse lies approximately 548 light-years away, everything we observe happened 548 years ago. If Betelgeuse exploded tonight, we wouldn't know for 5.5 centuries. Conversely, the star might have already exploded sometime in the 1500s, and the light from that explosion is currently racing toward us through the void. We could witness the supernova tomorrow, next year, or not for thousands of generations. This temporal uncertainty adds peculiar weight to observations of Betelgeuse. Every measurement, every spectrum, every image captures the star as it was in the late 1400s, during the early Renaissance, when Leonardo da Vinci was painting and Columbus was preparing his voyages. We're observing history, not the present, watching events that concluded before Shakespeare was born. Distance also affects potential hazards from the supernova. When massive stars explode, they emit gamma rays that could potentially damage planetary atmospheres. However, Betelgeuse's axis of rotation appears tilted relative to Earth, meaning any narrow gamma ray beams would miss us entirely. The supernova would pose no danger to life on Earth beyond the temporary inconvenience of having a second moon-bright object in the night sky for a few months. Some astronomers have investigated whether Betelgeuse might produce a black hole rather than a neutron star. The final fate depends critically on the core's mass at the moment of collapse. Cores between approximately 1.4 and 3 solar masses form neutron stars. More massive cores collapse directly into black holes. Current estimates place Betelgeuse's final core mass near the boundary, making its ultimate fate uncertain. If a black hole forms, it would do so silently, invisible except through its gravitational effects. The outer layers would still explode as a supernova, but the compact remnant would be a black hole rather than a rapidly spinning neutron star. Either way, the explosion itself would appear identical from Earth. The relationship between Betelgeuse's current size and its eventual fate is direct. The star's enormous radius reflects its advanced evolutionary state. Only stars in the final stages before core collapse expand to such dimensions. The extended atmosphere, the vigorous convection, the prodigious mass loss, all signal a star approaching the end. Betelgeuse's size is not just a measurement, but a countdown, a visible indicator of stellar aging that will culminate in spectacular self-destruction. Recent modeling attempts to refine the timeline by incorporating multiple observational constraints simultaneously. The star's mass, luminosity, surface temperature, pulsation periods, and chemical composition all provide clues about its internal structure and evolutionary state. By matching computer models to these observables, researchers can estimate how much fuel remains and how long current fusion processes will continue. But uncertainties compound throughout this process. Mass estimates vary by nearly a factor of 2. Distance measurements affect luminosity calculations. Pulsation analysis requires assumptions about internal structure. Each uncertainty propagates through the models, widening the range of possible outcomes. The discovery of Siwaha, the companion star orbiting within Betelgeuse's extended atmosphere, introduces additional complications. Interactions between the two stars might accelerate Betelgeuse's evolution. The companion is expected to spiral into Betelgeuse sometime in the next 10,000 years. If this merger occurs before Betelgeuse explodes naturally, it could trigger premature core collapse through the sudden addition of mass and angular momentum. Alternatively, the merger might simply be subsumed into the larger star's convective envelope with minimal effect on the core. We don't know enough about stellar mergers in this regime to predict outcomes confidently. What we can say with confidence is that Betelgeuse will explode. The physics governing stellar evolution are well established. Stars with Betelgeuse's mass cannot avoid core collapse. The iron core will grow until it reaches the Chandrasekhar limit. Collapse will occur. The supernova will happen. We simply cannot specify when with precision greater than tens of thousands of years. This uncertainty doesn't diminish the value of studying Betelgeuse. Every observation refines our understanding of red supergiant evolution. Every measurement constrains theoretical models. Every spectrum reveals details about surface composition, mass loss rates, and atmospheric dynamics. When Betelgeuse finally does explode, astronomers will be ready. Neutrino detectors are continuously monitoring for the characteristic burst that precedes visible light by hours. Alert systems will notify observatories worldwide within seconds of detection. Telescopes will slew to Orion, capturing the supernova's rise to maximum brightness across all wavelengths. The data gathered will advance stellar physics for decades. For now, Betelgeuse remains, still burning helium in its core, still pulsating through its 400-day cycle, still losing mass through stellar winds, still harboring a companion star spiraling inward through its atmosphere. The star's enormous size, between 640 and 764 solar radii, depending on measurement technique, stands as testament to the violent processes occurring deep within. Convective plumes larger than planets churn through the interior. The photosphere expands and contracts by distances exceeding Earth's orbital radius. Dust shells light years across mark ancient mass loss events. And somewhere in the future, perhaps soon by cosmic standards, the core will collapse, and Betelgeuse will end, as all massive stars must, in fire and fury that will briefly outshine an entire galaxy. Until then, we watch. Every clear night, Betelgeuse hangs in Orion's shoulder, pulsing through its cycles, broadcasting its instability across 548 light-years of space. The photons reaching Earth tonight left the star's surface in the late 15th century, when Leonardo da Vinci was sketching flying machines and the printing press was revolutionizing Europe. Those photons carry encoded information about the star's temperature, composition, velocity, magnetic field strength. Spectrographs decompose that light into constituent wavelengths, revealing absorption lines that mark specific elements. Doppler shifts in those lines track material moving toward or away from us, mapping the complex velocity fields across the photosphere. Modern interferometry achieves angular resolutions measured in milliseconds. Multiple telescopes separated by hundreds of meters combine their signals, effectively creating apertures far larger than any single instrument. The technique reveals surface features on Betelgeuse, bright hotspots where convection brings material upward, darker regions where cooled gas descends back into the interior. These observations show the star's surface is anything but uniform. It's a roiling, turbulent boundary between the relatively ordered core and the chaotic circumstellar environment. The hotspots themselves are enormous. A single convective cell can span a significant fraction of the stellar diameter, several hundred solar radii across. Material rises at velocities measured in kilometers per second, carrying energy from fusion reactions occurring deep within. At the surface, this material radiates heat into space, cools, becomes denser, and begins falling back down. The cycle repeats continuously, driving the star's variability and contributing to mass loss through stellar winds. This convective transport shapes the chemical composition we observe. Elements synthesized in the core through fusion reactions get mixed throughout the envelope, eventually reaching the surface where spectroscopy can detect them. The presence of carbon, nitrogen, and oxygen in ratios different from solar composition confirms that Betelgeuse has undergone dredge-up events. During certain evolutionary phases, convection penetrates deeper into the star, bringing fusion products to the surface. The observed abundances provide clues about which fusion reactions have occurred and how far the star has progressed through its evolutionary sequence. Size measurements continue improving as technology advances. The Atacama Large Millimeter Array in Chile combines 66 radio antennas to achieve unprecedented resolution at millimeter wavelengths. These observations penetrate the dust surrounding Betelgeuse, revealing structure invisible to optical telescopes. The star appears even larger at these wavelengths because we're detecting emission from cooler material in the extended atmosphere and nearby dust shells. Space-based observations avoid atmospheric distortion entirely. The Hubble Space Telescope has captured ultraviolet images showing Betelgeuse's chromosphere, the region just above the photosphere where temperature paradoxically increases with altitude. This heating mechanism remains poorly understood, but probably involves shock waves generated by convection or magnetic fields threading through the atmosphere. The chromosphere extends the effective size of the star beyond what optical observations suggest, adding another layer to the question of Betelgeuse's true dimensions. Infrared observations from space reveal the thermal emission from dust grains surrounding the star. These grains form when material ejected by Betelgeuse cools sufficiently for molecules to condense. The dust absorbs ultraviolet and visible light from the star, heats up, and re-radiates that energy in the infrared. By mapping this emission, astronomers trace the distribution of circumstellar material, finding shells and clumps that mark discrete mass loss episodes. Some shells are expanding outward at velocities exceeding 20 kilometers per second, carrying material that will eventually enrich the interstellar medium. The great dimming of 2019 to 2020 provided unexpected insights. Ground-based photometry showed the star dim to magnitude 1.6, the faintest recorded in modern times. Speculation ranged from imminent supernova to obscuration by dust. Follow-up observations confirm the latter. A massive convective plume had ejected material that condensed into dust, blocking light from part of the photosphere. The dust eventually dispersed or moved away, and brightness returned to normal levels. This event revealed how dynamic Betelgeuse's atmosphere really is. The ejected material weighed several times more than Earth's moon, blasted outward by a single convective event. The plume responsible measured over 1 million kilometers across, larger than the Sun. Such eruptions represent extreme manifestations of the convective processes constantly operating within red supergiants. They contribute significantly to mass loss, stripping away the star's outer layers over time. High-resolution imaging during the dimming showed asymmetric brightness distribution across the photosphere. The southern hemisphere appeared significantly darker than the northern, consistent with dust obscuration localized to one region. As months passed, the dark region evolved and eventually dissipated. These observations demonstrated that Betelgeuse's photosphere is not a smooth, symmetric surface, but a complex, changing environment where localized events can dramatically affect the star's appearance. The discovery of Sawarha adds an entirely new dimension to understanding Betelgeuse's evolution and eventual fate. This companion star orbits within what we'd consider Betelgeuse's outer atmosphere, at a distance of 4 astronomical units. That's closer than Jupiter orbits our Sun. The companion itself is no lightweight, 1.6 solar masses, likely an F-type pre-main sequence star still contracting toward the main sequence. How does a star survive orbiting inside a supergiant's extended envelope? The density of Betelgeuse's outer atmosphere is extraordinarily low, more tenuous than any vacuum we can create on Earth. Sawarha moves through this near vacuum, experiencing drag forces that gradually steal orbital energy. This energy loss causes the orbit to decay, spiraling the companion ever closer to Betelgeuse's core. Current estimates suggest the merger will occur within 10,000 years. What happens when they merge? The addition of 1.6 solar masses to Betelgeuse's envelope might trigger instabilities. The sudden injection of mass and angular momentum could disrupt the star's structure, potentially accelerating evolution toward core collapse. Alternatively, the companion might simply be absorbed into Betelgeuse's convective envelope with minimal effect on the core, where the fusion reactions determining the star's fate continue regardless. Binary interactions complicate stellar evolution models. Mass transfer between components, tidal effects, and eventual mergers all introduce variables difficult to predict. For Betelgeuse, the presence of Sawarha means that projections of future evolution must account for this companion's influence. Does it matter for the supernova timeline? We don't know yet. The physics of stellar mergers in this mass regime remains poorly understood, with few observed examples to calibrate theories. The name Sawarha, meaning her bracelet in Arabic, connects to historical observations of Betelgeuse. Ancient astronomers described the star's variability using metaphors drawn from jewelry and adornment. The companion star, orbiting within Betelgeuse's glow, does evoke a jewel set in a bracelet. The International Astronomical Union officially recognized the name in September 2025, following proposals from the Discovery team. This discovery emerged from careful analysis of periodic variations in Betelgeuse's radial velocity. Spectroscopic measurements track how fast the star moves toward or away from Earth by measuring Doppler shifts in spectral lines. A 6-year period appeared in these measurements, suggesting orbital motion. But Betelgeuse itself isn't orbiting. Instead, the companion's gravity tugs on the supergiant's photosphere, creating the observed velocity variations. Teasing out this signal required years of high-precision spectroscopy and sophisticated analysis to separate the companion's influence from Betelgeuse's intrinsic variability. Betelgeuse's size remains central to all these investigations. Every measurement technique, every theoretical model, every prediction about future behavior depends on accurately characterizing the star's physical dimensions. Yet, size means different things depending on what we're measuring. The photosphere, defined as the layer where optical depth equals unity, provides one reference. The chromosphere, where temperature increases above the photosphere, extends further. The dust shells, marking ancient mass loss, reach light years from the star. When we say Betelgeuse is 764 solar radii, we're specifically referencing the photosphere at near-infrared wavelengths. This represents the radius where the star becomes opaque to light at those wavelengths. Different wavelengths probe different depths in the atmosphere. Ultraviolet observations see higher, cooler layers. Infrared penetrates deeper, closer to the region where fusion energy emerges from the interior. The variability adds another complication. Betelgeuse pulsates with a dominant period near 400 days, physically expanding and contracting through a range exceeding Earth's orbital radius. During maximum expansion, the photospheric radius increases by roughly 60% compared to minimum. Measurements taken at different phases of this cycle naturally yield different size estimates. Long-term monitoring tracks these variations, revealing not just the pulsation, but also secular changes occurring over decades. The 15% shrinkage observed between 1993 and 2008 raised questions about whether Betelgeuse was undergoing long-term contraction. Subsequent observations showed the apparent shrinkage was likely part of longer period variability rather than permanent change. But monitoring continues, watching for any signs of evolution toward more advanced burning stages. Mass loss represents another critical factor. Betelgeuse sheds approximately 1 solar mass every 100,000 years through stellar winds. This material, enriched with fusion products from the core, expands outward at velocities of 20 to 30 kilometers per second. Eventually, it will join the interstellar medium, providing raw material for future star formation. The dust shells we observe mark episodic increases in mass loss, possibly related to strong pulsations or convective events. This mass loss gradually reduces the star's total mass, affecting its evolution. Less massive stars take longer to reach advanced fusion stages. More massive stars burn through their fuel faster. By shedding mass, Betelgeuse potentially extends its remaining lifetime. But the effect is modest compared to the overall evolutionary timescale. The star will still explode as a supernova, just perhaps slightly later than if mass loss weren't occurring. The iron core grows regardless. Deep within Betelgeuse, beyond the reach of any telescope, fusion reactions proceed towards silicon burning. Each fusion stage produces heavier elements: helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon. Silicon fusion produces iron, but iron cannot fuse exothermically. When the core becomes predominantly iron, fusion stops. Without fusion pressure supporting the core against gravity, collapse becomes inevitable. That collapse occurs on timescales measured in seconds. The core implodes, rebounding when nuclear density is reached. The rebound launches a shockwave that tears through the outer layers, ejecting everything except the collapsed core. The explosion outshines the entire galaxy briefly, radiating more energy in days than the star emitted over its entire lifetime. Neutrinos carry away most of the energy, detected on Earth hours before the light arrives. Betelgeuse's supernova will be spectacular. At 548 light-years, it's close enough to study in unprecedented detail, but far enough to pose no danger to Earth. The explosion will be visible in daylight, possibly reaching magnitude -12, brighter than the full moon. It will remain visible for months as the ejecta expand and fade. Every telescope on Earth and in space will observe, gathering data across the electromagnetic spectrum. That data will revolutionize our understanding of core collapse supernovae. We'll measure the shock breakout in real time, watch the light curve evolve, detect nucleosynthesis products in the spectrum, observe the formation of the neutron star or black hole remnant. The neutrino burst will arrive hours before optical light, providing advance warning and a unique probe of conditions in the collapsing core. Gravitational wave detectors might pick up signals from asymmetries in the collapse. But when? The uncertainty spans 10,000 to 100,000 years. Betelgeuse could explode tomorrow or not for millennia. The size measurements, the pulsation analysis, the spectroscopic abundances, the mass estimates, all constrain the timeline but cannot predict the exact moment. We watch and wait, knowing the star's end approaches, but unable to specify when with greater precision. This is where we find ourselves. Observing a star whose size challenges our measurement capabilities, whose variability reveals complex internal dynamics, whose companion adds unexpected complications, whose eventual explosion will illuminate supernova physics for decades to come. 764 times the Sun's radius, pulsating through ranges exceeding astronomical units, harboring a companion spiraling toward merger, approaching core collapse on cosmic timescales, but human uncertainty. Betelgeuse remains, for now, a red beacon in Orion's shoulder, visible to anyone who looks up on winter nights, carrying within it the seeds of its own destruction, vast beyond comprehension, yet finite, ancient yet young, dying yet still burning. A stellar monument to the violent beauty of the cosmos, reminding us that even the largest objects in the universe cannot escape their ultimate fate. Every photon streaming from Betelgeuse carries a message from the past, encoded in wavelengths that tell us temperature, composition, motion. The star we observed tonight appeared this way in the late 15th century, its light traveling 548 years to reach our telescopes. We're not watching Betelgeuse as it exists now. We're witnessing history, observing a stellar giant as it was when Leonardo sketched his inventions and Columbus sailed west. This temporal disconnect adds peculiar weight to every measurement. The 764 solar radius estimate describes a star that may have already changed significantly. The pulsations we track occurred centuries ago. The companion star Siwaha might have already spiraled inward, merged, triggered the very explosion we're waiting to observe. The light from that event could be racing toward us right now, scheduled to arrive tomorrow or next week or next year. Or perhaps Betelgeuse continues burning steadily, helium fusing into carbon and oxygen in a core we cannot see. Perhaps the star has tens of thousands of years remaining. Perhaps our distant descendants will witness the supernova, not us. The uncertainty doesn't diminish the scientific value. It amplifies the mystery. What we can state definitively: Betelgeuse is enormous. Whether 700 solar radii or closer to 1,000, whether measured at the photosphere or including circumstellar shells, this star dwarfs our familiar solar system. Earth would vaporize deep within the photosphere. Mars would be engulfed. The asteroid belt would disappear inside the star's outer layers. Jupiter might orbit near the surface, bathed in radiation that would strip away its atmosphere in days. Yet despite this vastness, Betelgeuse remains remarkably diffuse. 1/10,000,000th the Sun's density, more vacuum than matter in most of its volume. The boundary between star and space exists as a gradual transition rather than a sharp edge. Density decreases smoothly from the core outward through increasingly tenuous layers until eventually becoming indistinguishable from the interstellar medium. This structure enables phenomena impossible in denser stars. Convective cells larger than planets churn through the entire envelope. Companion stars orbit within the extended atmosphere. Stellar winds strip away solar masses of material over millennia. Violent eruptions eject moon masses in single events. The star pulsates through ranges exceeding astronomical units. All consequences of the extreme low density that characterizes red supergiants approaching core collapse. The size measurements will continue improving. New instruments, refined techniques, better theoretical models. Each generation of astronomers narrows the uncertainty. The current estimate of 764 solar radii represents our best knowledge given available data. Future observations might revise this upward or downward. The true value might vary depending on pulsation phase, evolutionary state, wavelength of observation, but the exact number matters less than what it reveals about stellar physics. Betelgeuse demonstrates how massive stars evolve, how convection operates in extended envelopes, how mass loss enriches the interstellar medium, how binary companions influence evolution. Every observation advances our understanding not just of this particular star, but of red supergiants throughout the universe. Somewhere in the constellation Orion, perhaps visible from your location tonight, Betelgeuse marks the hunter's shoulder. That reddish point of light, easily distinguished from surrounding stars, represents a volume containing hundreds of thousands of suns. A star so large it defies human intuition, so dynamic it constantly changes, so close to death that astronomers monitor it continuously, waiting for the explosion that will briefly outshine the galaxy. The supernova will come. The iron core will grow until it cannot support itself. Collapse will occur. The shock wave will tear through the star. From Earth, we'll witness brightness rivaling the full moon, visible in daylight, persisting for months. Every telescope will observe. The data gathered will advance stellar physics for decades. When that happens, whether tomorrow or in 10,000 years, humanity will witness one of nature's most spectacular events. A star we've observed for millennia, tracked through its variability, measured with increasing precision, will end. The explosion will scatter Betelgeuse's enriched material across light years, seeding the interstellar medium with elements forged in stellar fusion and supernova nucleosynthesis. That material will eventually contribute to new stars, new planets, possibly new life. But until then, Betelgeuse endures, still fusing helium, still pulsating, still shedding mass, still harboring its companion, a monument to stellar gigantism, to the physics of extreme objects, to the inevitability of stellar death. 764 times larger than our Sun, visible across 500 light-years, approaching the end of its brief, violent existence. The next time you look up at Orion on a clear winter night, find that reddish star marking the hunter's raised shoulder. Remember that what appears as a simple point of light actually spans distances that would engulf our inner solar system. Remember that the photons entering your eye left that star's surface 5 centuries ago. Remember that somewhere in that vast, turbulent atmosphere, fusion reactions continue building toward iron. Remember that this giant cannot last, that its size signals approaching death, that its eventual explosion will briefly transform the night sky. Betelgeuse stands as evidence that the universe operates on scales almost beyond human comprehension, that stars can grow so large they contain volumes measured in hundreds of millions of solar volumes. That objects separated by hundreds of light-years can still be studied in exquisite detail. That we live in an era when technology allows us to resolve features on stellar surfaces, to detect companions orbiting within extended atmospheres, to predict explosions that haven't occurred yet. The star will explode. The timeline remains uncertain. The observations continue. And somewhere between 640 and 764 solar radii from Betelgeuse's core, the photosphere churns with convection, pulsates through its cycles, and broadcasts its instability across the void, waiting for the moment when the iron core reaches critical mass, when gravity finally overwhelms all resistance, when Betelgeuse transforms from red supergiant to supernova in seconds.